official webinar. So good afternoon, ladies and gentlemen, and welcome to this webinar. My name is Tommy White. I am the sales manager here at the MasterSeries. The MasterSeries is a colossal program covering steel, concrete, timber, masonry, retaining walls, composite, portal frames, multi-story frames, single span beams. And I thought it would be a good place to start to look at what's included in our building design suite. This is our enterprise system where you have Revit integration, analysis, wind analysis, you have steel, composite, concrete, timber connection, dynamic analysis, detailing and drafting. All that. And all these little programs are modular. What we're looking at today is the connection design. We will first of all look at the connection design on its own, and then we'll also look at the connection design integrated into MasterFrame or even MasterPort. So we're just looking at one of our programs today. So just close that. I don't need that again. So into steel, into connection design, and we'll see that we design portal and multi-story connections to EuroCode 3.8 and BS 5950. Quite a lot of different types of connections, quite a lot of different SCI publications that we refer to. And let's just have a quick look at the program. So in the MasterSeries 2016-13 edition, I'm going to go straight into element design. So I'm in standalone mode, element design, and straight into connections. I'll see all the connections that I've done, and the one I'm after is this one. I could also have just selected it from using my favorites, but in this case we'll just go straight here and say get file. So here we go. A typical portal frame connection, 2.5 meter haunch, compression stiffener, bolts and end plate. You'll also notice that this compression stiffener is required because we are working to the EuroCode. We are using EC3 with the UK National Application Document. And we're looking at our first loading case, and we have 450, 300 and 100 as our forces applied. Looking at the information input, you'll see the forces as I described. End of haunch moment, we've reduced that down to 350. Column forces I'm not worried about. Column properties, I'm going for a 610 and it's grade 275. I'm going to change that to 355. So I can see I have several different grades built in, and I can add grades to my database. I also have, if we look at that one more time, all my UCs, but if I wanted to, I could come along and look at all my UCs, RSJs, IPNs, IPEs, W sections, all the standard British and European sections, and those W American sections. We also have dedicated databases for doing Japanese sections, for doing Russian sections, for doing American sections, and those are all available to you at no additional cost. So beam properties very similar. And then we have a haunch of 2500 on a haunch depth of 900 and a 7.5 degree slope. Bolts, we have no values, and that will then use the default values. So it knows for a 457 and a 610 that the 191 flange is not the smallest, it's the 178 flange, so it'll know to use 90 cross centers as the default for those. So a lot of things are using default values. And then the number of rows of bolts, upper and lower. So let's just look at all the different connections and then we'll go and do one. So typical eaves, an extended eaves connection, And then we have a double valley connection with stiffeners and a sloping compression stiffener, and we are asked it to align those so it's set out, the setting out point is 97 mil down, and that's the accurate value. We can also set our own value for offsets. So moving across, multi-story rigid with extended end plates and with stiffeners, and again double-sided with different heights and setting out points, 150 drop on the left hand side. And now we're into our second connection. So we've done 7 connections already, but they're all eaves connections, as we call them, beam to column flange. Now we're looking at apex connections, so your typical portal apex and your typical splice apex, including extended end plate and with stiffeners. And then thirdly, into our third connection, our base plate, and we have our typical effective area design of our base plate. And moving across, we can see with a slight moment and with a bigger moment, and we've had to put in 2 rows of bolts and get those out quite far. And we see here we have a failure because the screen's gone blue. So in fact our concrete's crushing and we need to increase the pressure or the base plate size to get a bigger compression area. But we're not designing this connection. Stiffened moment bases, very stiffened moment base with stiffeners in all directions, and quite a complex layout. And again, it's not that happy about the design because it's gone blue, and I can say why, and it's just telling us that our edge distance are quite close for the pullouts of the bolts. So now if we move across, we should be moving into a base plate with a shear stiffener, and now into the circular hull sections. I actually saw an article on the SCI LinkedIn yesterday, somebody asking, can you do, anybody know how to do circular base plates with moments? And the simple answer is yes, we do them very, very well. I even sent the guy an invite to this webinar. And then we have stiffened CHS and stiffened rectangular and slab rectangular hollow section base plates. Now we're into our last of our moment connections, our beam and column splices. Our beam splices with inner and outer bolts. Notice the staggering of the bolts in the web. And this is with inner bolts only. And yes, you can make them countersunk. So if I wanted to, I could have countersunk inner and outer bolts. Sorry, countersunk outer plates, and even countersunk with only inner plates if you really wanted to. And that's one with a part weld to ease fabric erection, where you can weld one side, and frequently you'll even weld one side in the bottom, and it's got an end plate here again for ease of erection rather than a web plate, all with the one configuration. And while you can do this connection, to the EuroCode this isn't very happy, and the very simple answer is it insists on there being a 25% moment capacity in the section, and it cannot resist 25% of its moment just with the web plates. So we'll not worry about that one too much. Coming along into my column splices, a non-bearing column splice, a bearing column splice with a single divider plate and cleats, a cap and base plate splice with external plates as well, and notice that we've elected to weld these so that we don't get our throat thickness grip thickness penalized due to the very large grip thickness. And then a pure cap and base. They work, they're not brilliant, but we can design them. And then you're into a hollow section splice, a circular hollow section splices. And now we're into the simple connections. Very quickly, going through those simple connections, we're into flexible end plate beam to beam. You notice that the notch is 35mm. That's less than the default, which allowed us to get this extra row of bolts in to make the connection work. Obviously, it's a wee bit annoyed, and the reason it's annoyed in this one is because the bottom end plate is infringing with the bottom flange. And as long as you keep them flexible, that's fine. But where you have these plates too thick and this down here, you do end up with a moment coming through. And then we have the similar, but it's a flexible end plates, but with the section dropped below the flange to get you full depth on that right hand side, and then single sided. And then we're into the fin plates in the similar mode, and even angled cleats. So for those fabricators who still like to use angled cleats because they're fast to fabricate, you can do those. And then finally we're into the beam to column connections. Now there's a lot of information here, and to help you, we even allow you to look at them one area at a time. So you'll see here that the bolts are pretty close to each other. So moving forward, you'll then see the fin plate in similar style. And if we go to that plan, you will notice that the fin plate has been notched in this side because of the web, because of the flange of the column, but has been notched top and bottom to facilitate fitting. Because if you've got two vertical columns, you can't drop a beam in between the two of them and miss this fin plate without a bit of jigging around or tilting of your columns, which is not very desirable. And then finally the same again, and we'll just look at that there with angled cleats. So those are all the different permutations of connections you can do, and that's not an exhaustive list. So what I'm going to do is I'm going to add in one more, and I'm going to add in a beam to column flange. And this is how quickly we can design a joint. I'm going to come along, beam forces. I'm going to take my default of 425, in fact, and I'm going to go for 100 and shear. That'll do. End of haunch moment, we'll go for 350. And then we don't need column forces. That's only when you have a multi-story and you don't know the values. Column properties 610 is fine by me. The beam properties, that's fine by me. We'll just change this slope down to 5-degree slope, and that just relaxes that a wee bit. Now, that's the basics, the section sizes, the section geometry, and the forces. So how do we know how to design this? Very simply. If the bottom is in blue, it means that there's a capacity problem. If we look at this, we will see that we're over 109% overstressed. So we need to put more bolts in, possibly. We need to put more rows of bolts. We need to maybe thicken end plates and other things. We also see here on this screen that we've got a blue because of dimensional problem, and that is because this bolt is too close. If I was to ask what's the dimensional problem, it would tell you bolt accessibility, and it's telling us that we are unable to actively rotate this around and in there. It's very tight, and we need to keep outside that region. So let's just go to our bolt rows, to our lower bolts, and the first row of bolts I'm going to make 90, and that's better but not good enough. I'm going to make it 100, and now it can be built. There are no clashes, there are no problems that way, but we still have our capacity failures, and we now see that there's a red dot here and there's a red symbol here, and if we ask for our symbols, we will see that the bolt is failing in tension. And we have, for an eaves connection, we have compression. It's actually, this one is column web tension or compression, so we're having a problem in here we need to sort out. So, getting rid of the symbols, we come along, and the first what I will do is go to main stiffeners, and end of hunch I will slip in a 8mm stiffener. And now that's no longer complaining, but I still have this massive overstressing. So bolt rows, double click, I'll put another row in it, 80, and I'll put another row at 80. So as we put the 3 rows in, we now see that we've gone down to 17% overstressed, but the failure symbol now moves, because that means that that is no longer, bolts are no longer the critical component. It will fail in crushing first. So go down to main stiffeners, bottom stiffener, and put in a 10mm stiffener, and now our connection very quickly, very simply works. Now, not all connections have only one loading case, and we understand that. So what I can do is I can add in a second loading case, which has got blanks, and I'm going to put a minus 250 moment with a minus 100 shear and minus 150 axial. And end of hunch moment is going to be less, so it won't really matter, but I'll put it in it as minus 200. And we will certainly print this case. So now we're going to look at the connection in reversal. And in reversal we can see that we're getting a moment capacity overstressing of 14%, but we also have a problem with our flanges. So let's look at our flange welds. So let's look at our flange welds. They're 8s, and that's a default. So go into welds, and the reason for that is twofold. So let's not worry about that first of all. Let us solve the compression problem. So I'm going to go to a top plate and put in a 10mm top plate. One of the nice things about the input system is that there are additional inputs, but without expanding, it will know what the sensible initial value is. So it'll know when I put in 10mm, that would be a thickness of stiffener. So I can do those abbreviations. So now we're down to 6% overstressed, and the welds are not as badly overstressed as well now. So what I need is more bolts down here. So bolt rows, low rows, and I'm going to put a second row up at, again, 80mm. So now the connection works. There's no more overstressing. Those bolts will do the job. And what's more, because of the distribution of forces, we no longer have the same load on our flange weld. So it was wise to not worry about the flange welds until we get the joint designed. Now, if I go back to case 1, we'll see in this case that has not caused a problem, but in some cases it could. So if you had several cases, it is handy to be able to scan through all the failures, all the loading cases, and if you watch the screen quickly, you will see that it goes to case 1 and then back to 2 and stops. So we're scanning all our loading cases and making sure none of them actually cause the problem. So that is the joint designed. I'm going to take a copy of that. So I'm going to copy this as joint 45, and we'll call it copy. And now what I'm going to do is going to reset all the input. So I only have bolts at 90 centers. Oh, sorry, that's the wrong button. Close that. I'm going to reset. It's the reset button, Tommy, that does a reset. So now I've got back down to just 2 bolts. And I'm just going to do a wee bit of initial twiddling. Sorry, bolt rows, and I'm just going to lift those up to the 100mm, so that's what it uses as start, and I'm just going to go to the upper rows and I'm going to lift that down to 80mm down. So just pulling this up and down. What I'm now going to do is I'm going to come along to the auto design. Okay, so just lock it in and click on auto design. So we'll redesign with an 80mm pitch and 10mm stiffeners and see what we can get. So here we go. And that's the design done. So if I look at the reversal case, it has done the design and it's given me a safe design. And if I do the ultimate case, it has done all the design. So for the two different loading cases, it automatically gave me a solution that worked for both of them. And if we had 6 or 7 or 8 cases, it would also have given me the design for all of those cases. So that is your moment connection done very, very simply. I've been playing around doing different things. Now, the default end weld is 20 mil. I don't think that that really is correct. So we could argue that we would get away with, say, a 10 mil end of haunch weld and a 6 mil web weld, and we'll see whether that works in this case and in that case. So 10 mil welds would work. Would you even get away in this configuration with only an 8 mil weld? And yes, you would. I wouldn't fancy going down to a 6 mil, but we will get away with an 8 mil weld, and that's in the BS. If I was back in the EuroCodes, I will see that I need a bigger weld. I'm going to need a 10 mil weld at least, and I do need my stiffener. This is one of the differences, I think it's the right word, one of the differences between the BS and the EuroCode is stiffening of compression zones is quite onerous on the fabricators. So let's go in and do another connection very, very quickly. I'm going to add another connection, and this time just do a simple base plate. And I'm going to come along and I'm going to do a base plate with a 25 kilonewton meter moment and a 350 axial, and I'm going to choose a UC section. Yes, and I think I better choose a better section than that. I'm going to choose something like a 203 by 52. And just a quick confirmation, yes, my 25 kilonewton meter moment isn't big because I can resist 200. And so base plate, let's go and make this slightly bigger. I'm going to make it 400 by 400. And we'll now see that a 400 by 400 base for a 200 by 200 column is working fine. Those are at 120 centers, and there's absolutely no problems. Now, one of the beautiful things about the EuroCode when we come to base plates is that we actually use a totally different stress block, and we use something called diffusion ratios and grout ratios for working out our crushing capacity of our concrete, or bearing capacity. So what we're seeing here is that the stress is coming in at 11.3, and that is for 25 concrete. In the EuroCode, as long as your concrete, your grout's within certain regulations, you more or less ignore the grout and design everything for the concrete grade. So I'm going to go up for 30 newton concrete, and you'll see that that's gone up to 14. So 14 on 30 is about just under 0.5, so it's a bit more than your 0.4. We can improve on that because we can use our known geometry to say that we actually know that the edge of the concrete outside the base plate is at least a meter, and we know that the concrete is going to be at least 500 deep, and suddenly we have this pad diffusion ratio has gone right up from 1.5 to 2.25 from the EuroCode, and brings us up to bearing capacity of 21.25, which can really help us. It helps us in that we can use a smaller area of base plate, and it also helps us because we can quite frequently use a thinner base plate. But this is all designed so quickly and efficiently. I'm going to add another case. So I'm going to add a case, and this case is going to be 0 moment, but it's going to be minus 200. So it's going to be 200 axial uplift. And we'll see that the pull-out cones are not happy. Well, first thing I would do is I would pull these pairs of washers a bit further apart. And I'm going to say the inner cross centers is at 200. Let's make it 250. So out there, 250. And then I'm going to go on the right hand side, do the exact same, and cross centers 250. So there we go. We have our bolts further apart. That's going to help us a wee bit. We're not failing on anything. The plate's still okay as thickness. What we need is more bolt pull-out cone. We need more depth of concrete. We need more shear resistance. If I come down and I look at my calculations here, we will see that we are working with a very low capacity, and that's because we're dealing with unreinforced concrete. So in the concrete, we also have the option to input steel. So top steel none. If I input steel of any size, we can go from cones to punching shear. So putting in 10s at 200 will increase my capacity. Cover to steel, I'm going to go for 50. But I still really need to get a lot deeper than 150 deep. So I'm going to go for 300. And that makes everything work fine. So could I get away with 250? No. 275. Well, I think I'll just stick with 300. So 300 pull-out cones now works. And it's telling us how close we can be to the edges to be safe. And we need to be at least 210 mil away from the edges of the plates to prevent us getting premature failure of the punching shear. That's your moment connections. This is all dealing with moment connections. What we can also deal with are the simple connections. And some people think, well, why? Because there's a table of simple connections. But they're only for the very simple configurations. If I come along and ask for a simple connection, which is a typical beam to beam flexible end plate, you can see that the default here is 50 mil. I can come along to my notches and say, actually, if I take that out and take that out, we can go all the way up to 28 mil. So I'm going to go 30 mil notch top, and if we need it, 30 mil notch bottom. And that's going to get me an additional bit of capacity. Now, we have notes, and that's because the bottom of the end plate should not project below the root fillet. But what I'm going to do is I'm going to go to my options, design options, and I'm going to tell it that we're going to use full depth. So apply and close. We don't need to worry about that error. We know we're using full depth end plates, and we can see immediately that everything under a standard load of 100 kilonewtons is working. I'm going to put the load up here to 350, and everything's fine. I'm going to go to the right member, and I'm going to increase that to 600. And now we get failure symbols down here. It gives us information just for one side because it is dealing with same set properties in each side, so it does all the design on the one side. So either we can say, well, what's the capacity? It's a wee bit silly, and reduce what we input, or we can actually go and try and design that out. Now, looking at what I put in, I think I have gone a wee bit over the top. The notch resistance is something that we don't have much control over. you would need to do some sort of manual stiffening on that to make that work if you wanted to. But naturally, one of the other options is to come along and drop the beams. Top flange offset, that's what I want, is 100 mil. Oh, better not. Minus 100, and that's too much, so let's go minus 50. Oh, that's a bit too much. Minus 25, which is just below. So you can see in this case you would never get without notches, so our section sizes are a wee bit overloaded for that size of shear. So the right hand beam, I'm going to change this to being 350 as well, and we'll see that most of it all now works, and we'll see that we're right up to getting quite high unity values on our sections, and it's telling us that our section limit would be actually about 540 in either side on this connection. So there we go, very simply our simple and our moment connections. And as I said earlier, you have a whole range of different simple connections for doing fin plates, cleats and things. One last thing I want to do is I want to do in standalone mode a beam splice. So I'll take my beam splice, and the first thing I'm going to do is go to beam properties, and I'm going to change this. And I'm going to change this to being a plate girder, probably of similar dimensions. So if I just take a wee note what my section size is, if I can scroll up here, what's my plate girder size? It's already gone away. If I go back to UBs, it should remember what that was. So 12s and 8s is for my flange thicknesses for my 457. So let's go and build ourselves a 500 deep plate girder of similar dimensions, and let's try built up. So we're going to make it 500 deep, and web thickness I think 10, top flange 200, top flange we'll make that 20, bottom flange width we'll make 200, leave it at 0 and it'll be the same, and bottom flange thickness I'm going to make 15. So it's asymmetrical, and I'm now going to go back up with this and I put in no root radius so it knows it's a welded section. If I put a root radius in, it thinks it's going to be some rolled section. So forces, I'm going to put a moment of, what is my moment capacity? 600. We're going to put a moment capacity of 350. And main shear I'm going to put in as 250. So we're going to need more bolts, obviously, and we're going to need to satisfy. So to the EuroCode, one of the things is you have to have plates that are similar thickness. So flange plates, top plates, and I'm going to go for 20mm plate. So it's taking one of the symbols away. Bottom plates, I'm going to go for 15. And it seems to be still a wee bit annoyed. I'm positive that was a 15. Yeah, it is a 15 bottom. And it must be saying the same thickness, never mind. Right, so we now need to make this work by putting in more bolts. So if I go and I say, right, let's look at the top and change it from 3 to 4 to 5. 5 row of bolts now makes this work. Let's look at the bottom. I'm only going to go from 2 to 3 to 4 to 5. 5 rows of bolts works bottom. Now the main problem now is our web capacity. Web capacity, we're going to increase its capacity in 2 ways. So first of all, coming down, web cover plates, and I'm going to go for 10mm plates. That's going to help a wee bit. And I'm going to go for 3 I'm going to go for four. Nope, not 6, Tommy. Going to go for 4. So that gets me another row of bolts. I'm going to make my plate 450 deep. So it's just in and no more. And since it's a welded section, 450 is probably too tight. I'm going to make it 425. Give it a wee bit of a gap. And I'm just okay in the end distances. I'm down to 59% overstressed. I think we'll have another row of bolts. Longitudinals, number of centers is going to be 1. And now my connection with those bolts all works. And that's my plate girder sized up for a beam splice. Now, one of the things we do, if you look at the bolts, there they are, is we're using high strength friction grip bolts. And that's fine. But some people just don't like to have to torque those up, and they want to use 8.8 bolts or even 10.9. So if I go 8.8 bolts, it looks okay down here. The calculations say, yeah, everything's fine. But I have a dimensional problem telling us that the SCI recommend you don't use loose bolts in beam splices. Now the reason for that is at the bottom of the screen we're going to have a rotation of around 1 degree. So if I go into splice rotation and I say this member, overall length of this member is in fact 12 meters and it's at 6 meters, then you'll see that we would actually end up with a rotation deflection due to the looseness of all the bolts of 48 millimeters. Now, one of the ways to solve that is to come along and put your bolts in not standard holes, but 1 mil close tolerance holes. And that brings the whole movement down to a more controllable 23 millimeters. And even better is under the beam properties, we could move it so that there's no beam gaps, so the flanges are initially bearing, and that halves the deflections again down to 12 millimeters. So even with the 1 mil close tolerance holes, you are going to get a 12 mil movement between the vertically down on a 12 meter span. So 1 in 1,000 is that physical movement, which isn't that bad. But you need to be aware of it. So that is the connections standalone. Output is very simple. We can come along and we can print our output to printers, and I am just going to come along and take the current joint plus maybe that one and that one and that one, and I'm going to print them to a printer, and it's going to be A4, and I don't know what my logo is, but I'll put it on and print, and off it goes, and it's now got 17 pages of output. And if I close my PDF writer, you will see, and here we go. It was a logo I did for a company called High Level who were using our software very recently ago. So there's your connection, your calculations, and your base plate, all output. You also don't need to take as many pages of output as that. If I go back to print and take, for example, current plus that one, and that one, I get asked for the graphics and summary only. And I could also say that I want a full page graphic each time. And this time when I go to print and print and then close 4 joints, 8 pages, and we'll see first of all the detailed joint, and then your results, joint, results, joint, results. So a little simple output, and that's because I asked for full page graphics. If I'd asked for just normal graphics, I would have got 1 page per connection. And that is great. That is the detailed output. We can also take this and we can send this out as a DXF file. I think I'm going to have fun and I'm going to spit them all out. I think, why not? Having a clue where they're all going to fit. I'm going to fit them in at 1 to 20 details on a huge big page. And I can get those in at 1 to 12 and a half. That's okay. And I'm going to export and load AutoCAD. So off it goes. It writes the files. It's now going to attempt to load AutoCAD. While it's loading AutoCAD, I'm just going to get myself started to the rest. I'm going to save that. No, I don't want to save my changes. And I now want to look at integrated design in MasterFrame. So the connections works superbly on its own, but it also works integrated. So a recent file I was playing with was this one, and I'll just get this file. And we'll talk about this file in a moment. Let's see, has AutoCAD loaded? Yes, it has. And we can see that somebody was playing around with my font sizes, and my titles are enormous. Everything else is realistic, but I think the titles for each one is quite large. It's quite funny. But there's your apex with all your information on the different layers. If I was to go to home, come on, Mr. AutoCAD. If you're gonna sleep with me, here we go. You could then see all the different layers that we have available to us. There we go. So you have all your joint layers. We also have layers for different things like our concrete design and our frame analysis results output and things. So I could, for example, take my bolts and I could turn off my bolt outlines, my center lines, and my bolts. Keep the current layer on. So there is some of the stuff turned off and then turned back on again. So I was playing with bolts layer. So that's all available to you. Obviously we would prefer not to have that scale of text for the main label, but that's something that is controlled within the MasterSeries, and somebody must have been playing and put in draw me very wide big text for the main labels. Okay, MasterFrame, a little MasterFrame building. Let's have a look at it. You can see that it's a steel frame building. The yellow members, for those who are unfamiliar, represent members that are composite, and the green ones are steel. The blue ones are bracing members because they're handled differently in design criteria. So what I've done, if I go into my editor, in this model manager, I'm able to go into groups and go into the connection design groups. So the model manager is part now of our MasterFrame Pro, where we do area loading and we do additional design functionality, and one of them is this design groups. And not easy to see when we're looking at the frame in solid, but when we're looking in wireframe, we can see that all these rafters are highlighted to be in eaves with a moment beam to column connection with these limits on their forces. These are all my axial bases, and I'm going to ignore anything within the net 10 kilonewtons of each other for the axial moments, and anything within 1 kilonewton for the moment. And that's to do with the number of loading cases. So if you had 6 joints with 6 cases each, they may end up with only having 7 cases because most of them are matching the first set very, very closely. So with our base plates, we have some flexible end plates, we have some beam to column fin plates. So using these, we can then analyze the frame very, very quickly it is analyzing 50 cases, and it's done 30, 40, 50 cases for me into design, and this is my integrated design connections. And here we go. I've already set these up for you, but I will set up another one for you. So this is looking, and I'm just going to pull this up a wee bit so you can see more of it. This is looking at this member and doing the eaves, but it's also looking at 1, 2, 3, 4 members that are also in green. Now these members here were meant to be in the same group, but there is something that's not consistent about them, and I suspect it's the fact that they have had their haunches taken off them. So those have haunches, but these yellow ones do not have haunches, and I did that on purpose just to demonstrate that we're able to distinguish and not blindly work with all the same forces. So we're not looking at the one set of forces anymore. We're looking at all the loading cases. So I'm just going to turn that off here and come back to my loading cases, and instead of having 1 to 38 ultimate cases, you can see it's now repeating for the next joint and the next joint and the next joint. So when I do a scan on this joint, it's actually going to scan all those loading cases and quickly find out if any of them have a problem in them. So that is where the flexibility of using integrated design and this MasterFrame Pro. So that's my first joint, very, very simple. My next joint is another apex, but this is on the one that it's on that's not linked to anything else. My third joint is a axial internal, and there was no others, so we'll see that when we look at the results that there are no other connections listed. Moving forward, we'll see now that we're looking at an external base plate, and it does have several in the background that are all got the same section size and orientation. So it's taking the moments from all those probably 12 different joints and putting them all in here in the one design, so we know that we're using, and it's listing the matching joints. So we have, as you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I guessed 12 connections, all being designed for the same. So whatever's in one is in all 12 of them without having to design them separately. And we'll see all the design is still there in detail. And then of course we have our column splices and our alternate column splices and our flexible end plates, and then here we have 1, 2, 3, 4 flexible end plates that are matching. Sorry, 3. That one is not matching, and even though it was meant to be in the same group. And just moving forward, we have another connection with the flexible end plates onto a column, and you'll see that there others are not matching because every single one is different section sizes coming into it, so it says no, do them all separately. So I'm going to take another joint and just do it from scratch. So I'm going to add in a joint, and I'm going to do a beam to column flange, and I'm going to choose to do over on this right hand side this one, and this is not got much on it. It's got a moment, but it's got no haunch. But let's see what we can get out of this with no haunch. We're not that far out, in fact at 33% overstressed. So unhaunched, I can come along and immediately add in another row of bolts at 80, and it now works. Let's check the other loading cases. So it's running through them all and says, yep, no. Because of the angle and everything, it's not getting any major moment coming into it. There is a little dimensional failure, And that was because there was a mismatch of different groups, because it doesn't match some other members in the group. It's doing it on its own. So that's not a big problem. That's just telling us that it's not been matched to anything else. And that's the joint design. It's as simple as that. So, ladies and gentlemen, that is the design of connections, either linked or unlinked. You can purchase the moment and simple connections, or just even the moment connections on its own, fully standalone, or with our frame analysis you can link it into our frames or our portals and do integrated design.